Let knowledge flow like a river without any hindrance. Don't make it like a stagnant pool. Hello everyone. I think all of you are okay. Once again I am PS Chatterjee with you, with my today's presentation commentary on IS-456-2000. Clause 9, Concrete Mix Proportioning. This is part 15 of the series. So we've been diving into Clause 9 of IS-456-2000, which focuses on concrete mix proportioning. But before we go any further, now the big question is, what exactly is concrete mix proportioning, and why is it so important? Imagine concrete as a recipe. Just like any recipe, the right proportions of ingredients are crucial for the final product. In concrete's case, those ingredients are cement, water, sand, and gravel. Number 1, strength and durability. The right mix ensures your concrete has the strength to withstand the forces it will be subjected to throughout its lifespan. A weak concrete mix can lead to cracks, failures, and costly repairs. Number 2, workability. A well-proportioned mix is easier to place and compact, saving time and labor on the construction site. Improper proportions can lead to a mix that's too stiff or too runny, both of which can cause problems. Number 3, cost effectiveness. By optimizing the mix design, you can use the exact amount of cement needed to achieve the desired strength. This avoids wasting expensive materials and keeps your project budget in check. In short, understanding concrete mix proportioning is key to achieving strong, durable, and cost-effective concrete structures. Clause 9 of IS-456-2000 deals with concrete mix proportioning. As you can see in the flowchart here, Clause 9 itself has 3 sub-clauses that provide specific requirements and considerations. You can then walk through the flowchart, explaining each sub-clause and its significance in concrete mix design. Sub-clauses under Clause 9, 9.1, 9.2, and 9.3. Title of Sub-clause 9.1, Mix Proportion. Sub-clause 9.1, further divided into 2 sub-clauses, 9.1.1, 4, determining concrete mix proportions, and 9.1.2, emphasize importance of information required. From 9.1.2, we have 9.1.2.1, specifying additional mix details. Now, subclause 9.2, title Design Mix Concrete. Subclause 9.2, further divided into 4 subcategory, from 9.2.1 to 9.2.4. 9.2.1 Emphasize quality control. 9.2.2 Focus on strength and workability. 9.2.3 Emphasize consistency, and 9.2.4 Understanding standard deviation in concrete. 9.2.4 further divided into 2 subcategory, 9.2.4.1 and 9.2.4.2. Now subclause 9.3, title, Nominal Mix Concrete. Next single branch from subclause 9.3 is 9.3.1. And 9.3.1 indicates adjustment of cement content in nominal mix. Alright everyone, time to return the favor. If you enjoyed this breakdown of concrete mix proportioning and think it might be helpful to your fellow civil engineering students, here's how you can be a real sport. Hit that like button. It lets me know you're out there and enjoying the content. Share this video with your civil engineer friends. Sharing the knowledge is what this channel is all about. Subscribe to the channel. There's a whole series on IS-456 coming up, and I don't want you to miss a thing. Now, let's get back to Clause 9 and see how it guides us in achieving those goals. As we saw in the flowchart on the previous slide, Clause 9 of IS-456-2000 guides us through achieving the desired concrete properties. But let's zoom in on Clause 9.1.1, which specifically deals with the methods for determining the proportions of cement, aggregates, and water. These methods are categorized as design mix concrete and nominal mix concrete. We'll explore these methods in more detail throughout the lecture. Clause 9.1 Mix Proportion. The mix proportions shall be selected to ensure the workability of the fresh concrete, and when concrete is hardened, it shall have the required strength, durability, and surface finish. Clause 9.1.1, the determination of the proportions of cement, aggregates, and water to attain the required strengths shall be made as follows. A. By designing the concrete mix, such concrete shall be called design mix concrete, or B. By adopting nominal concrete mix, such concrete shall be called nominal mix concrete. Design mix concrete is preferred to nominal mix. If design mix concrete cannot be used for any reason on the work for grades of M20 or lower, nominal mixes may be used with the permission of engineer in charge, which, however, is likely to involve a higher cement content. Now the question may arise, what is design mix concrete and nominal mix concrete? Design mix concrete, scientifically calculated mix to achieve specific strength, durability, and workability for your project. We may call it tailor-made recipe. And nominal mix concrete, fixed ratio of ingredients based on experience, suitable for lower grade concrete, M20 or lower, when design mix isn't feasible. We may call it predetermined recipe. To achieve consistent and reliable concrete, clear communication between different parties involved in construction is essential. Clause 9.1.2 of IS-456-2000 addresses this by specifying the information required for clearly defining a particular grade of concrete. This slide will detail these requirements. Clause 9.1.2, Information required. In specifying a particular grade of concrete, the following information shall be included. A. Type of mix, that is, design mix concrete or nominal mix concrete. B. Grade designation. C. Type of cement. D. Maximum nominal size of aggregate. E. Minimum cement content, for design mix concrete. F. Maximum water cement ratio. G. Workability. H. Mix proportion, for nominal mix concrete. J. Exposure conditions as per tables 4 and 5. K. Maximum temperature of concrete at the time of placing. M. Method of placing, and N. Degree of supervision. Clause 9.1.2 provides a solid foundation for specifying concrete. But what if there are project-specific requirements? This slide will introduce us to Clause 9.1.2.1, which offers some flexibility by allowing additional information to be included in the mix design when appropriate. Clause 9.1.2.1, in appropriate circumstances, the following additional information may be: A. Type of aggregate. B. Maximum cement content, and C. Whether an admixture shall or shall not be used and the type of admixture and the condition of use. Clause 9.2, Design mix concrete. Clause 9.2.1, as the guarantor of quality of concrete used in the construction, the constructor shall carry out the mix design, and the mix so designed, not the method of design, shall be approved by the employer within the limitations of parameters and other stipulations laid down by the standard. Clause 9.2.2, the mix shall be designed to produce the grade of concrete having the required workability and a characteristic strength not less than appropriate values given in Table 2. The target mean strength of concrete mix should be equal to the characteristic strength plus 1.65 times the standard deviation. Now we'll delve into clauses 9.2.3 and 9.2.4, which deal with two important aspects of design mix concrete: reusing past designs and understanding standard deviation. In this slide, explores these concepts. Reusing a previously successful mix design can save time and resources if certain conditions are met, as outlined in Clause 9.2.3. Clause 9.2.3, mix design done earlier not prior to 1 year may be considered adequate for later work provided there is no change in source and the quality of the materials. Clause 9.2.4, Standard deviation, the standard deviation for each grade of concrete shall be calculated, separately. Clause 9.2.4.1, Standard deviation based on test strength of sample. A. Number of test results of samples. The total number of test strength of samples required to constitute an acceptable record for calculation of standard deviation shall be not less than 30. Attempts should be made to obtain the 30 samples, as early as possible, when a mix is used for the first time. B. In case of significant changes in concrete, when significant changes are made in the production of concrete batches, For example, changes in the materials used, mix design, equipment or technical control, the standard deviation value shall be separately calculated for such batches of concrete. C. Standard deviation to be brought up to date. The calculation of the standard deviation shall be brought up to date after every change of mix design. Now the question arises, what is standard deviation? Standard deviation is a statistical measure that reflects how spread out the concrete strength results are around the average strength. A lower standard deviation indicates more consistent concrete strength. So far, we've focused on calculating standard deviation based on test results. But what if we don't have those results yet? Can we still design a concrete mix? The answer is yes, with a little help from clause 9.2.4.2. This slide will introduce the concept of assumed standard deviation, a valuable tool for quality control in concrete production when starting a new mix design. Clause 9.2.4.2, assumed standard deviation, where sufficient test results for a particular grade of concrete are not available, the value of standard deviation given in Table 8, may be assumed for design of mix in the first instance. As soon as the results of samples are available, actual calculated standard deviation shall be used and the mix designed properly. However, when adequate past records for a similar grade exist and justify to the designer a value of standard deviation different from that shown in Table 8, it shall be permissible to use that value. This is our Table 8, assumed standard deviation, clause 9.2.4.2 and Table 11. In this table we have two columns. First column stands for grade of concrete and second column stands for assumed standard deviation in Newton per square millimeter. Grade of concrete, M10, M15. Assumed standard deviation 3.5 Newton per square millimeter. Grade of concrete, M20, M25. Assumed standard deviation 4 Newton per square millimeter. Grade of concrete, M30, M35, M40, M45, M50. Assumed standard deviation 5 Newton per square millimeter. Note the above values correspond to the site control having proper storage of cement, weigh batching of all materials, controlled addition of water, regular checking of all materials, aggregate grading and moisture content, and periodical checking of workability and strength. Where there is deviation from the above, the values given in the above table shall be increased by 1 Newton per square millimeter. Here are a couple of ways to conclude your explanation of assumed standard deviation. Design mix concrete offers significant advantages. However, for lower grade concrete, M20 or lower, used in less critical applications, there might be a simpler approach. This slide will introduce nominal mix concrete, outlined in clause 9.3 of IS-456-2000. This method uses predefined ratios, making it a practical option for certain scenarios. Clause 9.3, nominal mix concrete. Nominal mix concrete may be used for concrete of M20 or lower. The proportions of materials for nominal mix concrete shall be in accordance with Table 9. Clause 9.3.1, the cement content of the mix specified in Table 9 for any nominal mix shall be proportionately increased if the quantity of water in a mix has to be increased to overcome the difficulties of placement and compaction, so that the water-cement ratio as specified is not exceeded. I think it will be better to explain water-cement ratio. In concrete, the water-cement ratio is critical. It's the ratio of water to cement by weight. A lower ratio, less water, generally leads to stronger and more durable concrete. Nominal mix concrete has its advantages, but maintaining the water-cement ratio is essential. The next part of clause 9.3.1, which we'll discuss shortly, highlights how to adjust the cement content if additional water is required during placement to ensure the water-cement ratio stays within the specified limits. Table 9, this table, based on clauses 9.3 and 9.3.1 of IS-456-2000, provides a quick reference for the proportions of ingredients in nominal mix concrete. The first column lists the grade of concrete, which indicates its target strength. The second column specifies the total quantity of dry aggregates, which includes both fine and coarse aggregates, per 50 kilograms of cement. This is a dry weight measurement. The third column shows the proportion of fine aggregate to coarse aggregate by mass. This last column indicates the maximum amount of water allowed per 50 kilograms of cement. For M5 grade of concrete, total quantity of dry aggregates 800 kilograms. Proportion of fine aggregate to coarse aggregate, generally 1:2, but subject to an upper limit of 1:1.5 and a lower limit, 1:2.5. Quantity of water, 60 liters per 50 kilograms of cement, or per bag. M7.5 grade of concrete. Total quantity of dry aggregates 625 kilograms. Proportion of fine aggregate to coarse aggregate, same as above, quantity of water, 45 liters per bag. M10 grade of concrete. Total quantity of dry aggregates 480 kilograms. Proportion of fine aggregate to coarse aggregate, same as above, quantity of water, 34 liters per bag. M15 grade of concrete. Total quantity of dry aggregates 330 kilograms. Proportion of fine aggregate to coarse aggregate, same as above, quantity of water, 32 liters per bag. M20 grade of concrete. Total quantity of dry aggregates 250 kilograms. Proportion of fine aggregate to coarse aggregate, same as above, quantity of water, 30 liters per bag. Note, the proportion of the fine to coarse aggregates should be adjusted from upper limit to lower limit progressively as the grading of fine aggregates becomes finer and the maximum size of coarse aggregate becomes larger. Graded coarse aggregate shall be used. Example, for an average grading of tine aggregate, that is, Zone 2 of Table 4 of IS-383. The proportions shall be 1:1.5, 1:2 and 1:2.5, for maximum size of aggregates 10 mm, 20 mm, and 40 mm respectively. In the example associated with Table 9 of IS-456-2000, a reference is made to Zone 2 of Table 4 of IS-383. The question then becomes, what is Zone 2 of Table 4 of IS-383? Zone 2 of Table 4 of IS-383 refers to in the context of concrete aggregates. IS-383 is a Bureau of Indian Standards specification for coarse and fine aggregates used in concrete. Table 4 in IS-383, specifically Clause 4.3 of the 2016 version, deals with the grading of fine aggregates, sand. It defines 4 grading zones, namely, Zone 1, Zone 2, Zone 3, Zone 4, and each zone has specific particle size distribution limits. These limits define the ideal range of sizes for the sand particles within that zone. Zone 2 represents a particular range of particle sizes suitable for certain concrete applications. To determine the exact size limits for Zone 2, you'll need to refer to the actual IS-383 standard. Thank you for watching this commentary on Part 15 of IS-456-2000. I hope you found this explanation helpful. My next video will explore Clause 10, Production of Concrete. Please don't forget to subscribe to my channel for more civil engineering related contents. If you have any questions, leave a comment below, and feel free to share this video with anyone who might be interested. Until next time, happy learning, and be well.